Okay, let's begin. Long weekend. And good news for the students is this Monday is a holiday, so no quiz, right? How about a take-home quiz? No, I've done that in the past, but let's, since we have covered, how many have we done? We have done 5 quizzes so far, so we are still on track to at least have 7 for the quarter. Typically, I try to hit at least 7, if not 8. And so we have 2 more weeks after next week, and so we'll be able to do that. So next week, enjoy your weekend. You won't have any quiz to do. The only deadline would be the homework, which I've set it for Monday. Again, my plan for today is to cover the rest of the theory and the concepts for chapter 3, inductor and capacitor, and to go over the examples for the problem. Several students have already started and completed the homework in advance. There is a portion of the homework which has already been covered. Most of them are conceptual short answer questions. So again, if students have not yet taken a look, please go online and take a look. There are 2 or 3 problems, but the others are just short answer questions. So, those topics have already been covered in class. So go ahead and get started on the homework if you have not already done so. All right, let's see. One note. Move this. Okay, so we stop here. Capacitor physical construction. So we saw for the inductor, the equations for voltage and current. Now we are going to look at the equations for a capacitor. The equations are very similar. The only difference is in the input consideration. For an inductor, we always talk in terms of the input current, which generates a voltage across its terminals. For a capacitor, we talk in terms of an input voltage, which generates a current through the capacitor. So I already covered this. Capacitor is a passive element, follows the passive sign convention or the passive reference configuration, right? Current always goes from high to low, plus to minus. We saw from the definition of a capacitor, charge, Q equals CV, dq or dt, rate of flow of charge is nothing but current, or current is nothing but the rate of flow of charge. So dq or dt gives us I. And hence, we can write current for a capacitor is directly proportional to the rate of change of voltage that is being applied across that capacitor. So I is equal to C dV over dt. Now, here you see the form of this equation is exactly the same as what we had for the inductor. For an inductor, it was voltage equals L di over dt, right? Here it is capacitor current, which is a function of the voltage. So capacitor current I is equal to C dV over dt. One more thing to note, the T is not required. When we looked at the inductor equations, I did not include a T. For the capacitor, I included. It simply notes that it is a function of time. So whether the T is included or not, the equation is still the same. It means the same. You apply it in the exact same manner. Okay. So whether it's included or not, it's the exact same equation. May or may not be included. Oftentimes, we take it one step further. There could be multiple inductors and multiple capacitors in a circuit. So notations could change depending on the number of components. Okay, so the notations could be simply I or IL or IC. Similarly, it could be V, VL, or VC. It will also be described as a function of time. So you could have I of t or IL of t or IC of t. If you have more than one capacitor or inductor, you might have L1, L2, L3, C1, C2, C3, and then you'd have one more subscript in there. You could have IL1 of T or VC2 of T. Is that clear to everyone? Again, so if the T is included or not, it is still a time-dependent function. Okay, it is still a time-dependent function. Okay. We saw for an inductor that if current is steady, it means it's constant, it's a DC applied current, then the voltage across the terminals would be 0 because di over dt is 0. Similarly, for a capacitor, if the voltage is constant, meaning if it's a battery or a DC input, once it reaches full charge, the current goes to 0. Okay, and that behavior is known as the steady state behavior because the input voltage or the input current is not changing with respect to time. Okay, so steady state behavior is when the capacitor or inductor reaches full charge, the final values of the voltage or the current is steady with respect to time. So steady state behavior, the capacitor acts as an open circuit. No more current is flowing in the circuit. Okay, inductor acts as a short circuit and capacitor acts as an open circuit. The equation again for the capacitor voltage follows a similar function, similar form as the one for the inductor current. You simply take your equation, the current IC of T is C dV over dt, and you integrate both sides. You integrate both sides, capacitor C comes out, goes on the other side, becomes 1 over C, and now you're integrating the capacitor current, IC. We go through the steps, and we have the exact same equation that we did for an inductor, except this time the current and I and voltage variables are changed, right? So capacitor voltage V of T, sorry, let me keep it simple. Capacitor voltage VC is simply the integral of the current IC. Okay. Capacitor voltage is the integral of the current IC. For an inductor, again, if you remember, it was the opposite. The inductor current was given by the integral of the voltage. So again, similar form of the equations, except the quantities are switched. All right, let's take a 10-second pause. Let me know if you have any questions. Any questions at all? Okay. Power and energy, again, same functions. Electrical power is given by the product of the voltage and current. So you simply plug in the values for the voltage and current in there, and you obtain P. Power for capacitor is C V dV over dt. Voltage times current, you plug in the equation for the current, and you get CV dV over dt. Energy is the same, similar to the inductor equation where it was half Li square. Here it is half CV square. Okay, the total energy stored in the capacitor this is once it reaches full charge. Okay, it's half CV square. Again, here the equations are a function of time. And again, you don't have to memorize these equations as long as you understand them and know how to apply them. Okay. So I have 4 examples in these slides. I think, let's see, 1, 2, 3, and 4. Yes. 1 and 2 are rather straightforward. I want to first finish off 3 and 4, and then I will come back to 1 and 2 if I have time. Otherwise, I will post them online. But they're rather straightforward. So, and then the most important point about these 4 examples, every single example references a capacitor. Okay, every single example in here references a capacitor, but the examples work exactly the same if it was an inductor. Hence, I have a very important note up here. It says all examples work exactly the same for both inductor and capacitor. Okay, it wouldn't matter if I switch this out with an inductor. The equations would be different, but the examples would work for both. Okay. So in this, now I will come back to 1 and 2 later. Let's go to 3 and 4. The reason is we're going to use a technique called piecewise linear analysis. Anyone use this technique or hear of this technique in your own fields? It's pretty, I wouldn't say common, but it's used in many scientific fields. And the homework problem is also based on a similar example. So basically, if you apply a DC voltage or current to the inductor or capacitor, we know at the end what our final values would be, right? If you apply a voltage to a capacitor, we know that the capacitor will charge to that voltage. Now, the value of the capacitor while it is charging, value of the capacitor while it is charging, those equations we'll look at in chapter 4. But if it's a DC voltage, meaning DC that doesn't change and it stays constant, we know what the value would be. Similar for an inductor, if we apply a DC current, we know what the value for that current is going to be. But if we have a function like this, where the value of the input voltage or current changes with respect to time, then we apply these equations to determine what the voltage or the current would be. Okay, so this first example, you are given the voltage and you're asked to find the current. In the second example, you're given the current and you're asked to find the voltage. Again, these reference a capacitor, but you could switch out examples 3 and 4, and you could use an inductor and they would work exactly the same. All right. So let's begin. What do we do in piecewise linear analysis? Well, exactly as the name suggests, you're going to take the input signal and you break it up into small pieces. Okay. Now, as a function, there is no singular description for this signal or this function that you see here. Okay. We cannot describe this in any mathematical terms directly. So we'd have to derive or write it down. Okay. In examples 1 and 2, we are simply given a mathematical function, cosine. Here also, natural log, exponent function. Okay. So we can simply apply mathematical techniques, calculate, and find out the voltage and the current. Here, however, we don't have any choice. There's no standard description. So what we're going to do is we're going to break up into smaller pieces, and each piece will have a linear relationship with respect to time. So on the surface, we can easily see there are 2 distinct time periods. We can go from 0 to 6 and 6 to 8. And each piece has a linear relationship with time, meaning it is a straight line. Does everyone see that? Right? You break it up and look only at this piece. Actually, let me change the color. Only this piece, going from 0 to 6 milliseconds. It is a straight line. It's not a constant value, but it is a straight line. So it has a linear relationship with respect to time. So we are able to describe it in terms of the line equation, right? We can simply describe it in terms of the line equation. Mx plus b. Look familiar? Y equals mx plus b, or you might use a different variable. You're describing the quantity on the y-axis, m is the slope, and this is the y-intercept. Is everyone familiar with the equation for the line, right? In this case, you will see the beauty of the equation, or the beauty of using this technique, is that since the relationship is linear, all we have to do is describe the slope of the line. Because a capacitor voltage, if you describe the slope of that voltage, it automatically gives you dV over dt. So for a capacitor current, all you'd have to do is multiply the capacitor with the slope of that line, and you'd have your answer. And that is the beauty of this technique. Piecewise linear analysis, you break it up into individual pieces, and each piece has a linear relationship with time, which is on the x-axis. So if you describe the slope of that line, it automatically gives you dV over dt. Let's take a pause. Let me know if that makes sense, and let me know if you have any questions. Any questions? Does it make sense? Right? Okay, so let's look at time value from 0 to 6. And this is milliseconds, so always be careful about the unit prefixes. Okay, unit prefix milli. All right, so between the time 0 and 6 milliseconds, I want to describe the line. In this case, I don't need to describe the entire line. I just need to write out the slope of the line, which, if you all remember, slope is given by, you take two coordinates at the end of those lines and just plug it in. So the slope of the line in the first portion, y2 would be 24 volts minus 0, and x2 is 6 milliseconds minus 0. Which is what we have here. 24 divided by 6 milliseconds. And that's it. That's the slope of the line. That's dV over dt. Right? Slope of a line. V is on the y-axis. And then all you do is you multiply that slope with the capacitance, and you have your answer for the current for the first time period. So I, or IC, is simply C times dV over dt, or C times M. Let's call this time period 1. So I'll call this M1. This is C times M1 gives me 5 microfarads times M. Plug in the value, and this is what we obtain. 5 microfarads into 24 divided by 6 milli. You solve that and you obtain an answer or a value of 20 milliamps. 20 milliamps. Take a look at the equation, the calculation. Let me know if you have any questions or if it doesn't make sense. Any questions? Easy enough? Hopefully. One important note is that always pay attention to the units. It's milliseconds. So if you neglected to take the milli into account, your answer would be wrong and you'd have 20 amps instead of 20 milliamps. Okay. So always extract as much information as you can from every problem, from the image, from the problem statement, from anything else that is given in the problem question itself. Okay. Here, if you miss taking the milliseconds, your answer would be incorrect. So make sure you do that. Keep that in mind. Is the first time period clear on how to obtain the capacitor current? Okay. Second time period. Let's call it 2. And this would be 6 and 8, or between 6 and 8 milliseconds. 6 and 8 milliseconds. Here, my value is going from 24 volts down to 0. So my input voltage is going from 24 to 0. So it's going in the opposite direction. And so now my slope, I'll call this M2. And M2 in this case would be 0 minus 24 divided by 8 minus 6 milliseconds again. That would give me minus 24 over 0.002. And this would be volts per second. So it's coming down at the rate of minus 24, or sorry, it's coming down at the rate of 24 volts for every 2 milliseconds, or 12 volts per millisecond. Then again, simply multiplied with the capacitance. So this would be IC1. IC2 would simply be C times M2. It's again 5 into 10 raised to minus 6 times M2. And I'd obtain a value of minus 60 milliamps. So this would be 20 milliamps. Okay, 24 divided by 2 times 5. 12 times 5, 60 milliamps. Make sense? Then when you plot it, this is what you would obtain. The value for the current between 0 and 6 is a fixed constant value, 20 milliamps. And so that's what we see here, 20 milliamps. And then time period 2, let me call this 1 and 2. This is 1, this is 2. And time period 2 is minus 60 milliamps. So constant line, which eventually then goes to 0 once the voltage returns to 0. Okay. The current stays pretty much constant. All right, any questions? Any questions at all?
So this is not unique, okay? The capacitor inductor, of course, you know, we encounter in electrical engineering, but the math that is involved is not unique. The math is straightforward. You would have used the same technique, or you may use it in the future in your own fields. You have your equation. It does not matter what the function is, whether it's representing a capacitor or an inductor or some sort of mechanical valve. It doesn't really matter. Once you see this function, recognize what it is giving you, determine what equations you need to use, plug in the values, and then solve. Okay. All right, think over it. Let me know if you have any questions. Any questions at all? Nope. Does it make sense? All right, then. Let's move on to example 4 of piecewise linear analysis. This time we are given the current and we are asked to find the voltage. Capacitor value is different. It's given as 4 microfarads. Okay, capacitor value is 4 microfarads. And we are given the current. So now we are looking at it from the other side. We are going to integrate. So the mathematical function we'll apply is integration. If you flip, then example 3 for an inductor would be integration. And example 4 for an inductor would be the slope of the line, the derivation. Again, the examples, all 4 examples work equally for both capacitor as well as inductor. Okay, so in a function like this, it's your job to recognize it and see if you can apply piecewise linear analysis. In this case, the answer is yes. If I break it up into 2 parts, each part has a linear relationship with time. The second part actually is simply constant, -8. Okay, -8 microamps. And this is a little tricky to see, but this top point is 16 microamps. Okay, 16 microamps. So we'll use the same technique. We'll describe capacitor current IC in terms of a line. So we use the line equation to describe the capacitor current. The 2 time periods, let's see, T1 is from 0 to 2. This representation, by the way, simply means T is between 0 and 2. T takes on any value between 0 and 2 or less than 2. And then T2 is between 2 and 4. And again, it's milliseconds. So do not forget that. 0 to 2 and 2 to 4. Let's tackle T2 first. Time period 2 is constant, DC. So we simply write the value for time period 2 as -8 microamps. -8 microamps. And that's it. It's T1, T2. And then, of course, greater than 4. We don't even need to write it, but since I have it, I'll just label it as T3. T1, T2, and T3. T2 is straightforward. We don't need to describe it except in terms of the constant value. Let's look at T1. My 2 points. M1 would be 16 microamps minus 0. Divided by 2 minus 0 milliseconds. Actually, it makes it clearer. So 8, my slope is 8. 8 into 10 raised to 3. Again, do not forget to take the units. Oh, sorry. So you have microamps and milliseconds. So this comes out to be 8 into 10 raised to minus 3. Minus 3 amps per second. Or you could write it 8 milliamps per second. Either way is fine. Okay, either way is fine. And then equation of the line for the time period 1, T1, B is 0, X is T, and Y is I. I simply get I, or I of T is 8 into 10 raised to minus 3 T plus 0, which is what we have here, right? It's a function of time. T is the variable. Make sense? Any questions? Any questions? Paul? Okay. Then we plug those values into our equation. So our equation states that V, voltage for a capacitor, is the integral of the current I in the integral time period. Since we want to find the value in terms of T as a function of time, I'm going to change the limits of the integral to 0 to T. Okay, 0 to T, because I want to find the answer as a function of time. So I'm going to set the limit of the integral also as 0 to T. And since I did that, I'm going to change the variable to X. Can be anything. You could use A, B, C, D, whatever you wish. X, Y, Z. X seems to be the most common, and so I just use X, Ix times dx. Okay. Again, note, since I want to find the value of the voltage and the current, voltage as a function of time, I'm setting the limits of the integral as 0 to T. Okay. That zero is not necessarily 0 on the axis. Remember what I said earlier. Time T0 is the time at which you begin your analysis. Everybody remember that? So in this case, my time period goes from 0 to 2. 0 is my start point, and 2 is my end point. So for time period T1, T0, my start point is 0 milliseconds. and hence the limit of the integral starts from 0 and goes to t. T is basically the variable because I want to find the value of the voltage at any given point in time between 0 and 2. Does that make sense to everyone? I want to make sure everyone understands before I move on. Any questions? Okay. So T0 is 0 milliseconds. I'm going to go ahead and plug the values in there. Capacitor value is 4 microfarads, so 1 over C. Then I have my line equation 8 into 10 raised to minus 3. And the limits of the integral 0 to t. My initial value V0 is 0. So I can cancel that out automatically. Okay. Can cancel it out automatically. The problem statement nor the figure gives me a value for the initial voltage. Okay, so if it's not given, you can safely assume it to be 0. Okay, so there is no stored energy in the capacitor. The initial stored voltage would be 0. I don't have to worry about that term. I only have to worry about this. Okay, simple integral as far as things go. 8 is a constant, comes outside. And so it becomes 8 into 10 raised to 3 or 10 raised to minus 3. Divided by 4 into 10 raised to minus 6. And here, of course, it becomes square over 2. And then limits of the integral 0 to t. Take the 2 outside. Everything cancels out. All you're left with is 10 cubed. And then you plug in the limits of the integral and you end up with t squared. So 10 cubed times t squared is your answer, which is what we have here. Ten cubed times t squared. Understand this. The math could be simple, it could be complicated. That just depends on the circuit parameters and the circuit layout and the boundary conditions that we apply, right? But that math is the same for all engineering fields. It doesn't change. Okay, so I will show the math here, and even in the exam, the math that you're going to look at is not going to be much, it'll be similar to what we do in the homework and be similar to what you do in the class here. But as an engineer, if you're outside, the math could be very different. But the equations are still the same. So your job as an engineer would be to take those equations, analyze the problem correctly, and then find the value for that equation. Okay. Again, as I said, the math could be anything depending on the circuit values, the circuit parameters. The equations remain the same. Does it make sense? Right? Okay, 10 cubed times t squared. If I now want to find the value of t anywhere between 0 and less than 2, I simply plug in the value of t. If I wanted to find the value of t, if I wished to find the value of the voltage at 1 millisecond, I would plug in t equals 1 millisecond. If I wish to find it at 1.1 milliseconds, I can still do that. Simply plug in t as 1.1 and find the value. Function of time, right? This equation is only valid for the defined time period. Okay, it's only valid for that defined time period. When we get to the next piece, the next portion, the value changes. But we do need to find the value at 2 because the energy stored in that capacitor at the end of the first time period is the initial stored energy for the second time period. Right? We are breaking it up into two pieces. So when you begin the analysis for the second piece, the capacitor already has some stored energy from the first time period. Does everyone understand that? Right? And so we need to take into account that initial stored energy. That is V0, time T0. And hence I was harping on this. T0 is not the beginning of time. It is simply the time at which you begin your analysis. For the first time period, it was 0 seconds or 0 milliseconds. For the second time period, it is 2. Okay, your second time period begins at 2 milliseconds. So let me write that down. T2 is between 2 and 4 milliseconds. So the point at which we are beginning our analysis, which is T0, is 2 milliseconds. It is not 0. Is that clear to everyone? Makes sense, right? Students always have a hard time sometimes, especially not in this class, but especially if we are doing an EE problem, there might be like more than 2 pieces, like 3, 4, 5, 6, 7. And so for every single piece, you have to take the preceding initial stored energy into account. Okay. In 201, I do not usually, I usually would not go more than 2 time periods. But if you did, in real life, if you did encounter something like this, then you know what to do. The beginning part of your analysis, if there was a further value given beyond 4 milliseconds, then let's say time period 3 would begin at 4 milliseconds, and so on and so forth. So T0 would change for every single time period. That's the most important point. Okay, so for this one, T0 is 2 milliseconds. So we need to find V0, the initial stored energy, which would be at voltage at T equals 2 milliseconds. And the equation for the voltage at 2 milliseconds was given in the previous time period. And so we simply plug in the value of T as 2 milliseconds and you solve. Plug in the value of T as 2 milliseconds and you solve for the voltage at 2 milliseconds. You find it as 4 millivolts. I got about 6 minutes left, so I'm going to rush through this a little bit. Is the concept clear? Okay, so then we take those values, we plug in here. V2 is basically the voltage at 2 milliseconds. And then C is 1/4 microfarads. In this case, the integral is simple because it's a constant, -8 microamps, right? -8 microamps. You simply plug it in, and then of course this is V0, which is 4 millivolts. Solve the integral, and you get an expression which looks like this. It's still a function of time, so -2t times, or sorry, plus 8 into 10 raised to -3 volts. Still a function of time, changes. That's your final answer. Again, this is a constant, so it comes outside, right? 8 into 10 raised to -6 is a constant, comes outside. You simply again get x squared over 2. The 2 also comes outside, cancels out. So you again end up with 0 to t. You plug in the limits and you get -2t plus 8 into 10 raised to -3 volts. Now you can take that expression and you can plot the voltage as a function of time. Okay, as a function of time. So the first one was here. 10 cubed times t square. So if you wish to plot this, depending on the number of data points you take, you could go 0.1. And if you have a computer, obviously it's very easy to plot. MATLAB, it's like a single equation. You plot in the values and it just spits out a value. You can do this in Excel. You can do this manually, which is how we used to do it, which, you plug in every single value like t equals 0.1, 0.2, 0.3, and so on and so forth, depending on how many data points we want. And you calculate for each one, and then you simply plot it on a graph or a chart. Okay. I will not ask you to do anything like this in an exam, but as engineers, even in your own field, I would presume that you would have done this before. Yes, no, taking an equation and just plotting it out, right? And so when you plot this is time period 1. This is 2. And this is T1. You have 2 separate equations for both time periods. You simply plug in the values of T and you plot it out. There are also equations for power and energy. But again, it's not something that I really go in depth in this class. Okay, questions. Did it make sense? Yes or no? Yes, I got 2 thumbs up. Thanks. All right, let's see, few minutes left. Inductors and capacitors add up the exact same way as resistors. Inductors add up the same way as resistors. Capacitors add up the opposite of resistors. So if you have 2 inductors in series, you can measure the inductance. If this is L1, if this is L2, the total LT, is simply L1 plus L2. 2 inductors in parallel. Or let me add LEQ, since we are using EQ, LEQ, L1, L2. LEQ is simply the reciprocal of the reciprocals. Capacitors add up the exact opposite. So if you have 2 capacitors in parallel, then you simply add them up. C1, C2, CEQ. CEQ is equal to C1 plus C2. And if you had 2 capacitors in series, the CEQ between the outer terminals is given by the reciprocal of the sum of the reciprocals. Okay. So again, inductors add up the exact same way as resistors, capacitors exact the opposite of resistors. And then the final slide, I simply have a summary of all the equations for this chapter. All right. So again, also has series and parallel connections right there at the end. So consider this chapter completed. Covered the theory, we covered the equations that govern it. We solved 2 examples. The examples 1 and 2, I will just solve them and I will either post the note in the slides here or I would post a video, either case. If I do a slide, it will simply be added and you'll have it available at your end in the class notebook. Okay. So any questions? Any questions at all? No? You're eager to get your weekend started? In one of the previous sections, so I'm going to leave you with this. Student asked me about music and I said I'd share some music from India this week. So this is a song. I don't know if you have heard of this, but there is this Norwegian dance group started by a couple of brothers many years ago. And well, I'll let you listen on this verse. So this was the wedding of one of those brothers. I'm gonna stop there. So these are a couple of brothers from Norway. They took the song that was from an Indian movie, and they did a performance at one of the brothers' weddings. This was a couple of years ago. Before they did this, they had performed they performed in America's Got Talent, a couple of shows around the world. But this went viral very, very quickly, and it became like a TikTok sensation. So there are people all around the world, from like Korea to Africa to America, South America, Europe, everywhere. We're doing like TikTok style performances, like short performances, and posting it online. But if you wish to check out the original song that is based on, so the group, they call themselves Quick Style, and the song basically is Kala Chashma, which literally just translates to sunglasses or black sunglasses. Kala is black, Chashma is glasses. So Kala Chashma is black glasses, and it's from this. Enjoy your weekend. I will see you all on Wednesday. All right.